Okay, welcome. We're going to continue on in chapter 14, where we left off. Okay, so excuse me. We've been talking about pH. The pH scale is acids and bases. So we were talking about the Bronsted-Lowry definition of an acid and base. Again, a Bronsted-Lowry definition: an acid is a proton donor, while a base is a proton acceptor, which is the H plus. And when we do have the Bronsted-Lowry sort of definition of an acid and base, it does give way to conjugate acid and bases and sort of conjugate acid base pairs that develop. And remember that an acid on the left-hand side of the arrow is related to the conjugate base on the right-hand side, and they are related to each other by 1 H plus, while the base on the left-hand side is related to the conjugate acid on the other side, also by 1 H plus difference. Remember that it can only be 1 H plus difference in order for them to be pairs. Anything more than that, they technically are not acid-base conjugate pairs. We talked about Kw, which is H plus concentration times OH minus concentration equals 1 times 10 to the minus 14. They are related to each other, so as the H plus concentration goes up, the OH minus concentration goes down, and vice versa. So we can use that to figure out the H plus concentration in the solution, or the acid part, if you will, and the OH minus concentration and the basic part of the solution, if you know one of the other sort of values there, either H plus or OH minus. We also talked about the pH scale, which runs from 0 to 7 to 14. Less than 7 is acidic. More than 7 there is basic, and at 7 is neutral. And we could calculate the pH by taking minus the log of, no, it's not it. pH is minus the log of the H plus concentration. There we go. And we also can calculate the pOH, which is a similar scale but runs opposite, and it measures the hydroxide concentration, which is OH minus. So we take minus the log of the OH minus concentration. And that's sometimes helpful because, as we saw, the pH plus the pOH does equal 14, which means, if you only have a certain amount of information, you can calculate either the pH or the pOH, subtract 14, and then obviously get whatever value you're looking for. We also saw that if you take the pH value, you can calculate the H plus concentration for a solution, and that's the inverse log of the minus pH, and that essentially is the shift log button on most people's calculators. The 10 and the caret usually will pop up. And you can also do that for pOH. If you have the pOH, you can get the OH minus concentration by doing the same calculation, the inverse log of the minus pOH. Again, this gives you a variety of ways you could sometimes get the pH of a solution or the H plus of a solution. You could use Kw, you may not have to use Kw. So where we left off was, I think, right here. And in certain cases, you may not be given just a generic H plus concentration or OH minus concentration. You may be given an actual formula for an acid. And what we see here on the screen is two problems, and we're both going to assume that they are strong acids and strong bases, and we want to calculate the pH of these guys. So why don't you take a couple of minutes and see what you come up with. So both of these guys are going to be strong acid and a strong base on the bottom there. So why don't you take a moment and see what you come up with while I go try to find out where I threw my calculator. Okay, so let's take a look here. So at the first one, HNO3 is nitric acid. So that's one of those strong acids that we talked about. And again, because it's a strong acid, when we have the HNO3 in solution, it is going to break apart 100% into H plus and NO3 minus. And in terms of pH, obviously the important part here would be our H plus concentration, as the pH equals minus the log of the H plus concentration. So we do know that the entire thing here is 2 times 10 to the minus 3 molar. And if we need to know the H plus concentration in this case, it is a 1-to-1 relationship between those two things. And as you hopefully you remember, concentration works that way. So that means that the concentration of the H plus ions are 2 times 10 to the minus 3. By the way, the concentration of the nitrate ions would also be 2 times 10 to the minus 3, although we don't really need them here in this problem. So really in this case, we actually do have the H plus concentration because it's a strong acid. So we just need to put that in. pH is equal to minus the log of 2 times 10 to the minus 3. And looks like we will end up with 2.7, it looks like, as our pH. And it does make sense. 2.7 is definitely acidic, so that would obviously make sense in terms of our answer. Any questions on that first one? Now, on the second one here, we do have a little bit of a different situation happening. We do have a base, and this is barium hydroxide. So when barium hydroxide breaks apart, it's going to break apart into a barium ion and actually 2 hydroxide ions. Again, that T will come to the front. And we again know the concentration of the whole thing, which is 1.8 times 10 to the minus 2. And in terms of pH, the OH minus is important here. Not going to get us to pH, but will get us to POH. And it is a 1-to-2 relationship, which means the concentration of hydroxide actually would be 2 times 1.8 times 10 to the minus 2. The reason I went to 1 decimal place above was, if you remember, for pH, the number of significant figures in this number is 1, sig fig. And that would give us 1 decimal place as we go this way. So that's why I rounded like that. So it's 1 to 2. So we do have to actually multiply the concentration by 2 to get to the correct concentration. And that would be 2 times 1.8 to the minus 2. And it looks like we get something like 0.036 molar. And again, that equals our OH minus concentration. So again, we can calculate the POH from that. And that's going to get us, looks like 1.44 as our POH. And we would want to take 14 minus that to get to our pH. 12 and some change, I think. 1256. Where's my thing? There it is. 1256. That also does make sense. Obviously, 1256 is basic. Barium hydroxide would be a base. And again, if 1.44 you thought was a pH, again, shouldn't make sense to you. Any questions on any of those things? Again, remember that when we go from concentration to pH or POH, the sig figs in the concentration is how many decimal places we should have, and vice versa. If we go backwards from a pH or a POH to the concentration, the number of decimal places tells us how many significant figures the concentration should have. Any questions on either of those things there? So sometimes you may not just be given a kind of generic H plus OH minus. You may be given the formula for a strong acid or a strong base, and you essentially just need to figure out either the H plus or the OH minus concentration. All right. So let's talk a little bit about what happens when we deal with weak acids. So weak acids, which are kind of weak electrolytes, they do not 100% break apart in solution, and they do set up an equilibrium. And again, we can really simplify the equilibrium by getting rid of the water. And as we talked about last time, if we get rid of the water, we get rid of the H3O plus and it becomes H plus. So this guy here and this guy here are pretty much the exact same reaction. HA is a generic sort of formula used for a weak acid or an acid in general. And we can write our Ka expression to add to our ever-growing K list. It is essentially the exact same things we've done before. It is our products over our reactants. And the A part tells us it's a weak acid, dissociation constant, or an acid ionization constant. And A stands for really acid. So as the Ka value increases, so does the strength of the weak acid. So let's just talk about that for just a second, just to make sure we're clear. If we have a larger Ka value, or you're comparing Ka values, the larger Ka value will be the stronger weak acid. So obviously a weak acid will still be even the strongest weak acid will be weaker than a strong acid in that sense. So when we have a large K value, again, that means we have mainly products or more products. And when we have mainly more products in a weak acid, that means we have more free H plus. More free H plus means that's your definition of an acid, right? Is the ability to produce H plus. So the greater the Ka value, the more products, more free H plus, the stronger the weak acid. So this is one really big way you can determine whether or not an acid is a strong acid or a weak acid is by the Ka value. Would I expect to find a Ka value for a strong acid? And hopefully the answer that you are saying to yourself is no. Yeah. Remember that a strong acid, and as we'll talk about later on, a strong base, they're strong electrolytes, which means they 100% break apart in solution and pretty much all head in one direction. There's nobody coming back the other way like we have here in our reversible reaction. And thus they are not able to set up that equilibrium because they pretty much completely dissociate from each other. As opposed to, say, a weak acid, which will mainly stay together in solution and break apart a little bit into ions, but will mainly stay together, but still able to produce some H pluses. So that's a really big hint that if you see a Ka value, you're dealing with a weak acid. And, if you can't find a Ka value, you're probably dealing with a strong acid. And here's a table from, I think, your book, or a version of your book, and some Ka values. You may have to look them up on a table to do certain problems. They may not always be given to you in the actual problem, but you can kind of look them up in the table. So how do we solve sort of weak acid problems when we're trying to figure out the pH? We essentially do them just like a normal equilibrium problem. We pretty much just do, you would be given a table of Ka values or Kb values or any of those type of constant values that you would need. Yep. We approach these pretty much just like a normal equilibrium problem, and we're going to have to do an ice table. Really, the only difference sort of between a sort of Ka problem and like a regular equilibrium problem is at the end of the irregular equilibrium problem, we're interested in what everybody's concentration is at equilibrium. Typically, when we do sort of a weak acid problem, we're interested in the H plus concentration because that's going to allow us to get to the pH. So we do it the exact same way. So we'll go through this one together here and see how we do. So we'll do our initial ice table. In this case, we're only given 0.5 molar here for our HF. Just like normal, we could assume that our products are going to be 0. The change will be minus X, and plus X. Again, like normal, if we're not given anything on the product side, probably a pretty safe bet to assume that it is, again, heading in this direction. We're going to carry these guys down. So that's going to give us 0.5 minus X, X, and X. Just like previously, we're then going to take those values and put it into our equilibrium expression here. And when we do that, we get x squared on top. We get 0.5 minus x on the bottom equals 7.1 times 10 to the minus 4. So since that is a small value of k, I'm going to assume that x is equal to 0. Give it a go, see what happens. And remember, when I do that, I can't get rid of all the x's, so I will have x squared over 0.5 equals 7.1 times 10 to the minus 4. So what we're going to do is multiply the 0.5 to the other side and do a little square root action. So 7.1 to the minus 4 times 0.5, square root of it. And we do end up with an x value here of 0.0188. Remember that when we do make the assumption, we do want to make sure that we check it to make sure it's okay. And again, to check it is we take our x value, we divide it by what we were going to subtract it from, and multiply by 100. And it looks like you get something like 3.8%, which means the check is good. Remember, we're looking for 5% or less. So since that check is good, that essentially means that this is our x value. And again, as we talked about, since we're looking for pH, that's really the only thing we're interested in this table. So x does equal the H plus concentration, and that gives us 0.0188 molar. Again, you can assume that x is equal to 0 when you have a small value of k. Small value of k means that we would mainly have reactants at equilibrium, so the change part will not be that big. So you can assume that x is equal to 0 in that case, but again, you do have to make sure you check it. It won't always work. Remember, small is pretty much anything less than 1. So anything with a negative exponent on the k value, you can give it a shot. Again, may not always work, but a lot of times it will work. Anything that's greater than 1 is considered large, so you can't do that assumption. So now that we have our H plus concentration, we can put it into our pH, and that would get us minus the log of 0.0188. And that looks like we are going to get a pH of 1.73, give or take, with some rounding. That's a really bad one, as I just lost my one there. There you go, 1.73. And again, that is acidic, so that's good, since this is an acid. As we talked about last time, you don't have to do the assumption. If you want to kind of do the quadratic formula, you could do that as well. Again, you should get pretty much the same answer. There might be some slight variance with depending on how you round. For example, if I rounded 0.019, I might get a different number, obviously, than what I got here. Any questions on that? So again, a reminder that when we do these, as we can see here, and as we talked about previously, we do want to make sure that we check. You can see they rounded to 0.019. Now, just a reminder that it will not always work, for example, and it is really concentration dependent. So for example, we did the exact same problem, but the only difference is we started with 0.05 molar instead of 0.5 molar. And what that would get you is pretty much the same setup. And when you would assume that x is equal to 0, you would end up with x squared over 0.05 instead of 0.5 like we had in the first problem. And if you did the check and all that good stuff, you can see that you would end up with 12%. So in this particular case, you would not be able to solve this problem like we did. You would have to go back like we talked about and use something like the quadratic to solve it. So again, always a good idea to make sure you check everything. Won't always work. We'll talk a little bit about why this doesn't work as well in this chapter, but just sort of a preview of it. When we take something that's 0.5 molar versus something that's 0.05 molar, there's a big difference in terms of those concentrations. So The 0.5 molar is more concentrated than the 0.05 molar. It's kind of like when you have, say, a whole pizza, for example. If somebody takes one piece of pizza out of the brand new pizza, not a big deal, right? Because you started with a bunch. But if you had like 2 pieces left and somebody took one piece, right? Same amount they're taking, is going to be a bigger percentage of your whole pizza, right? At that point. And that's sort of the same idea here. Because our concentration was so small on the second example, when we do, even though the change is small, that small change is still significant compared to where we started with versus the 0.5. Any questions on that? So this sort of goes over the main ideas, but essentially we do approach this the exact same way as a normal equilibrium problem. Let me see. You might be right. I don't know. So you're talking about this example here. Truth be told, what I wrote, and actually what the people who did this slide from the textbook wrote, they're both technically wrong. The original concentration, right, if you look at it, actually is 0.5 molar, which is one significant figure. So really the correct answer in terms of significant figures here actually should be actually just 1.7, because the only number we're dealing with really is here. And technically speaking, that's one significant figure, which would give us 1 decimal place. So I guess I was sort of closer-ish than that. Other questions on that? Okay. So we do these problems, like I said, just like we do our regular ice tables, and we ignore the auto-ionization of water. So what that means is for our problems and in this class, and I think most of the textbook online sort of problems that you do, we sort of ignore water's influence on the H plus concentration, OH minus concentration. Now, there's some people in some books, when they do these type of problems, they do take water into account. So what does that mean? That means that, for example, if we did like the concentration of H plus in our acid, and that concentration was significantly smaller than just the regular concentration of water would give you in terms of H plus, some books will actually just go with the water sort of value. So we don't worry about water or its sort of contribution to H plus or OH minus. We almost just look at our acids and bases as just kind of separate entities, and there's no contribution to water. So you don't have to worry about that. But sometimes you might come across somebody that does take it into account. So in books and study guides, sometimes they do talk about those things. We do our ice table, but again, pretty much the thing that we're interested in, like I said before, is the H plus concentration, or when we talk about bases, the OH minus concentration, because that's going to allow us to get to our pH in that case. So why don't you give this one a go? What is the pH of a 0.122 molar monoprotic acid whose Ka value is 5.7 times 10 to the minus 4? Monoprotic is 1 hydrogen they could give away. So HA is a sort of generic formula you could use for monoprotic. So take a couple of minutes and see what you come up with. Okay, so let's take a look and see how we're progressing. Even if we're maybe not finished, let's just kind of make sure we're all on the same page and on the right track. So again, if you're not given a formula, you could use this again as your monoprotic acid, and that's going to break apart into a lot of lines apparently. H plus and A minus. Maybe I can clean up some of those lines there. All right, so we got a Q. Now we're going to do our initial and our ice table. So the only number we're given is 0.122, 0 and 0 here. Again, safe to assume we're going left to right. So minus x plus x plus x. And that's going to give us 0.122 minus x, x, and x. So the ice table, obviously very similar to all the other ice tables we've done. This is going to go into our Ka expression, which in this case would be H plus A minus divided by HA. 5.7 times 10 to the minus 4, that equals. So that's going to give us x squared over 0.122 minus x equals 5.7 times 10 to the minus 4. So you can assume x is equal to 0 here. And if you do that and you check it like you hopefully should have checked it, you will see that this is bad. It's like 6 point something percent. Just over 5, but still technically bad based on our sort of code of 5%. So if you did assume that x is equal to 0 in this case, and you didn't check it, you should have, because technically this is too high at 6, I think it was like 6.3, 6.8%, something like that. So we do need to solve this quadratic-like. And if we do that, if we multiply the bottom to the other side, and we get something like x squared equals 6.95 times 10 to the minus 5 minus 5.7 times 10 to the minus 4 x. And if we kind of combine everybody together, we get a quadratic sort of equation of x squared plus 5.7 times 10 to the minus 4x minus 6.95 times 10 to the minus 5 equals 0. Again, we're going to put that into our quadratic formula, which again is our x is equal to b squared plus r minus square root of b squared minus 4ac divided by 2a, and that actually is minus b, right? Minus b plus or minus, there you go. No squared there. So minus b plus or minus the square root of b squared minus 4ac. And if we put all that in there, we do get 2x values. And if you put our numbers in, you get x is equal to 8.06 times 10 to the minus 3. Or you get minus 8.64 times 10 to the minus 3. Any questions up into that point? So again, here we're interested in our H plus, which is here. So obviously we cannot have our negative concentration. So this number cannot be right. That means that the positive number should be correct. And that would be the concentration of H plus, which would equal 8.06 times 10 to the minus 3. That's going to go into our pH minus the log 8.06 times 10 to the minus 3. And if we do that, looks like 2.09 as our I'll get my head working with the writing part of it. 2.09. There we go. 2.09, which is our pH. Any questions on that part of the calculation, where any numbers came from, why we did anything? Any of those questions? Now, to be truthfully honest with you, if you just went straight to the assumption and didn't check it, in this particular example, you would get an answer pretty close. I think you get like 2.08 if you just went with the assumption. Again, won't always be that close, so do make sure that you do check the assumption. The 6.95, that came from, so we're talking about this number here. That came from multiplying 0.122 by 5.7 times 10 to the minus 4. So we basically multiply this entire thing to the other side, and that's where these numbers came from. The pH, yeah, in this case, it should be actually, yeah, you would be right on that. It is 3 significant figures, I guess, in that case. So yeah, you could take it to 3 decimal places, which technically, I guess, would be in this case. I remember what my other number was. I think there's a 4 at the end, yeah. How do you check if X is good or bad? Is that what you're asking? So if you're checking the X value is good or bad, you essentially, for example, in this one, if we assumed X is equal to 0, we would take 0.122, we would times it by 5.7 to the minus 4, and we would take the square root of it. And if we did our assumption, the X value we would get was 0.00834. And we would take that and divide it by what we were going to subtract it from, which is 0.122, and times it by 100. And if you did that, you get 6.8%, something like that. You assume the reaction was going left to right because like we did with our regular equilibrium problems, you were not given any information about the product side. So you would assume that the reaction is proceeding from left to right in that case. So just like we did with the regular equilibrium problems, if all you're given is just the concentration of the HA, you could assume it's heading to the product side. Other questions? Okay. And by the way, when you did this guy on the left, you got 6.8%, which again, just slightly too high, and just happens to be in this case. You get an answer pretty close. All right, so why don't you try this one, calculate the H plus concentration, and while you're at it, why don't you calculate the pH of a HCN solution that has a Ka value of 6.2 times 10 to the minus 10. When you assume X is equal to 0, it's always the zeros that you're either going to subtract off from a number, or the zero that are the X that you're going to add to a number. It's never really the X by itself. So it's usually the one either you're going to minus from a number or add to a number. So like an example, that last one was 0.122 minus X. That would be the X that you would assume is equal to 0. Okay, so let's take a look, see how we're doing. So again, by the way, we do know it's a weak acid because we do see a Ka value associated with it. So we know we should go our ice table approach here. Again, it's going to break apart into H plus and Cn minus. Again, we're only given the concentration of HCN, which is 0.01. Nothing on these guys, so we'll assume 0. Also going to make us safely assume that we're going left to right here, and our x's will look like this. That means at equilibrium 0.01 minus x, x, and x. Any questions on the ice table? I move some stuff around so I have somewhere to kind of write. Let's go that way with that. All right. So now what we want to do is go into our Ka expression. And again, our Ka expression is going to be our products. This is our H plus and our Cn minus divided by our HCN. And that will equal our Ka value of 6.2 to the minus 10. So putting that in, we're going to get x squared over 0.01 minus x equals 6.2 times 10 to the minus 10. Again, here the K value is small, so we can assume that x is equal to 0. And again, as the earlier question was, it will just be this x here. Obviously, you can't get rid of all the x's, otherwise you got nothing to solve for, but it is typically the ones you subtract or add to a number, and that's going to give you x squared over 0.01 equals 6.2 times 10 to the minus 10. We're going to multiply the 0.01 to the other side and also take the square root of it. And if we do all that, looks like you get something like 2.5 times 10 to the minus 6. I can find where I'm writing there. We do want to check it, so we're going to take that 2.5 times 10 to the minus 6. We're going to divide it by 0.01 and times it by 100, and you're nowhere even near 1%. It's super small. So again, to check it, I get it over there, maybe in that area. We're going to take this, divide it by 0.01, times it by 100%. And again, the check is good. Happy face. So that does mean that this x value, again, is going to be our H plus concentration from our table. And that means that the pH will equal minus the log of 2.5 times 10 to the minus 6. And gets you something like, that's not the right answer, minus the log of 2.5 to the minus 6. That's better. 5.60 looks like in this case, which is acidic. And again, our H plus concentration would be this here, which is really what the question was asking. Any question on any of those steps where we found anything? Okay. So Ka problems are essentially just equilibrium problems, and really the only difference is you're just going to kind of find that H plus concentration so you can get into that pH. Everything else pretty much the same deal. Okay. So let's talk a little bit about percent ionization. And percent ionization tells us how much the acid, for example, has broken apart. And when an acid breaks apart, we sometimes say it dissociates. We also sometimes say it ionizes. Basically, it's how much H plus comes off, right? So that's basically what makes something an acid, is how much H plus that will come off. And we could calculate the percent ionization. And believe it or not, the percent ionization calculation is actually what we do to check our assumption. So when we make our assumption, we take the H plus concentration and divide it by the initial concentration of the acid. And that's essentially how we do percent ionization. So the percent ionization is the amount of H plus, free H plus, divided by the initial amount of the acid times 100%. A strong acid will 100% ionize, as you can see here, all the way across. Now, a weak acid will have different percent ionization, and it is based on concentration. So at lower concentrations, we have a higher percentage of ionization occurring. When the concentration gets larger, we have a lower percentage of ionization occurring. So that's sort of back to that idea of what we were talking about earlier. Again, if your concentration is big to start with, if you lose a little bit of it as it ionizes, the change is not going to be all that much, as opposed to if you started with just a small amount to begin with. If you lose a little bit of that small amount, that is a bigger percentage of the whole. And that's why we see a greater percent ionization as the concentration is smaller. Also, why sometimes your assumption will not work because of the concentration that's there and the Ka value that's associated with it. So again, that's why it's always important to check your assumption, and you could also calculate what's known as a percent ionization. So let's take a look at a problem like this. A solution of 8 molar formic acid is 0.47% ionized. In this case, we're actually going to be looking for the Ka value. So you can approach this very much like a regular problem, except that obviously you don't have a K value, but you can still sort of work on it that way. So if we take our acid and if we take our formic acid here, which obviously is a weak acid because we're looking for a Ka value, we'll break apart into H plus and HCOO minus. And we can even do a kind of ice table just to kind of put us in the right sort of way like we've been doing. So we know that we're starting with 8 molar of this guy and nothing of these guys. And if we were going to do a regular ice table, we would do minus X plus X plus X, which means when we get down to equilibrium, we would have 8 minus X, X, and X. Now, normally we'd put this into our Ka expression, which is the concentration of H plus, concentration of our formate, divided by our formic acid. And if we do that, that gets us X squared divided by 8.0 minus X. And that equals, I'm not sure, because that is kind of what we're looking for in this particular case. So that's where the other piece of information given to us comes into play. It does tell us how much percent ionized this acid is. And as we just saw on the previous page, percent ionization is equal to the H plus concentration divided by the initial acid concentration times 100%. So we have that it is 0.47% ionized. We don't know what the H plus concentration is, but we do know that the initial concentration was 8 molar times 100%. And sorry about the extra line there. So we're going to multiply the 8 over to the other side. So we're going to take 0.47 times 8 divided by 100, or essentially you're taking 8% of, I'm sorry, 0.47% of 8, basically, or 0.047. And that gives us a H plus concentration, come here, H plus concentration of 3.76 times 10 to the minus 2 molar in that case. It does not like when I write up in that area, huh? Get rid of maybe some of those lines, a little bit better. Maybe see that. All right. So we were able to use the percent ionization to figure out the H plus concentration, which is good. And we now know if we go to our table, the H plus concentration actually equals X. And again, this X is pretty much all the X's in our ice table. So now that we know what X is, we have this X, we obviously have this X, and we have this X. So we basically can put it into our expression. And if we do that, as I run out of some room, we'll go over here, I'll try. Let's see if it'll let me write it this way. We're going to take X squared, which is 3.76 times 10 to the minus 3 squared, divided by 8 minus 3.76 times 10 to the minus 3. And that should give us our Ka value. So if we do that, we're going to square it. We're going to divide by 8 minus our X value. And hopefully it will equal one of those nice numbers that we see on the page here, 1.8 times 10 to the minus 4. Which looks like it is number 2 here is the right answer. So this is a problem that's very similar to what you did actually in that equilibrium experiment where you sort of figured out X and sort of worked your way backwards to figure out the equilibrium constant. So same idea in this particular problem using the percent ionization. Any questions on where any of those numbers came from? Okay. Then let's talk about the other type of weak situation that we could come across, and that is a weak base problem. Let's come back. And in a weak base problem, when we do write the equations for a weak base, like I mentioned earlier, we do typically put water in there. And again, the ammonia here is going to act as the base. It's going to accept the H plus from water and make ammonium hydroxide, which is, as we talked about yesterday in lab, ammonia is really a source of ammonium hydroxide, which is a source, as you can see here, in the aqueous solution of hydroxide, basically. So we can write a KB expression for it. It'll be our products over reactants, just like normal. And again, we're not going to include water in there. And that, again, is what's known as a KB expression. Same thing with our Ka value. As the Kb value increases, so does the strength of the weak base. So the higher the Kb value, the stronger the weak base is. But obviously, just like our acid, the weak base is not as strong as a strong base. And just like our acids, we will not have a Kb value for a strong base because a strong base is a strong electrolyte, will not set up an equilibrium. We solve these problems just like we've been doing in these last few examples. We're going to use an ice table. The only difference is you don't have H plus in the equation. You will have OH minus, and you will need to solve for X. In this case, X will actually equal the OH minus concentration. That will then allow you to calculate the POH, and then you can get to the pH from that. So there's going to be choices down the road where you got to choose, should I be using like a Ka value? Should I be using a Kb value? So really the simplest way to think about it is to look at the equation. And that's why it's important to know how to properly write these equations, because if you properly write the equations, and like we see here on the screen, if you look on the product side and you see OH minus there, that's a very big hint that you probably should be using a Kb value if you're doing a calculation. And vice versa, if you look at the previous ones that we did in those previous examples, for example, even here, when we look on the product side, what we see is not OH minus, but we see H plus or H3O plus. So when we see H plus or H3O plus on the product side, we should use a Ka value if we're doing a calculation. If we see OH minus on the product side, we should be using a Kb value. Any questions on that? Here's a table. Again, a big hint is if you see a KB value, it's going to be a weak base. So why don't you give one a go here? We're looking for the pH of the solution that starts with 0.15 molar, has a KB value of 5.6 times 10 to the minus 4. So see what you come up with, and we'll talk about it in a few minutes. Okay, so let's see how we're doing. So this is a KB, so we'll take what we're starting with here. So C2H5NH2. And when you write the KB or basic type reactions, this is one where you probably do want to put the water. People always sort of struggle as to kind of what to react it with. So the water sometimes helps you visualize what's going on. Again, a base means he's going to donate over, right? And that's going to give you your C2H5NH3 plus, your OH minus. And again, important to be able to write these reactions so you can clearly see the OH minus. You know you're on the right track here. We're going to do our ice table. 0.15, 0 and 0. Change going to be minus X, plus X, and plus X there. Again, I apologize for the extra lines that seem to be coming out here today. Now, you also notice that I pretty much have ignored water, and I would be ignoring water because it's not going to really participate here in the equilibrium. So I always find it's good not to try to put numbers or letters in places where you might want to actually use numbers and mess up. So might as well just ignore water as it's obviously a liquid, right? All the rest of them are aqueous. I was just too lazy to apparently write it. You know, X and X. Yeah. Any questions on the ice table there? This is going to go into our KB. So our KB, again, going to be our products. Divided by our reactant. And that's going to equal, where is that at there? 5.6 times 10 to the minus 4 in this case. We're going to put in our values, so that's going to give us x squared divided by 0.15 minus x equals 5.6 times 10 to the minus 4. And I just want to kind of see, do I have, I do, okay, good. I do have another page, so that's good. All right, so we're going to do an assumption here, and we're going to assume that x is equal to 0 here because we do have a small k value. And that gives us x squared divided by 0.15 equals 5.6 times 10 to the minus 4. When we do solve for our x in that case, we get 0.00917. And if we take that and divide that by 0.15 and times it by 100, we get 6.1%. So divided by 0.15 times it by 100 equals 6.1%. That means sad check, not so good. So again, this is over 5%, which technically means it's too big. So we do have to go back and solve it a different way, which is the quadratic for us. So coming up here, going back to our original guy there, x squared and 0.15 minus x equals 5.6 times 10 to the minus 4. We're going to multiply the entire bottom to the other side, and that will get us x squared is equal to 0.00084. And just ignore the extra lines coming out for free today. 5.6 times 10 to the minus 4x in this case. Yeah. Combining everybody to one side gets us x squared plus 5.6 times 10 to the minus 4x minus 0.0000084 equals 0. Putting it into our quadratic gets us something like x is equal to minus b plus or minus the square root. If you, let's see here, if you clean up the square root, I believe you get 0.000336 inside. And then if you take the square root of it, you get 0.0183. So again, that's 336 there. And that's going to be all divided by 2 in this case. That's going to give you 2 x values, and that would be x would equal, if we did our positive, our plus, 0.000, too many zeros, we'll turn that into an 889, right? So 0.00889 as an x value. Get rid of that extra line maybe. All right, try that again. So that's a 0 and that's a 0. So 0.00889. And if you do the other one, you do get a negative number. So negative 0.00943, give or take. So if we go back to our table, we see that x is equal to, we go back to our ice table, x equals the OH minus concentration. And obviously that means that we cannot have our negative value as one of our answers. That means that the 0.00889 should be the correct answer. And that means that that should equal, again in this case, not the H plus concentration, but the OH minus concentration. And that's going to allow us to get to the POH. So the POH minus the log 0.00889. And if you do that, looks like 2.05 for our POH. And then obviously our pH would be 14 minus that. 1195 looks like a winner there. And that would make sense as obviously it is a base, and that is a basic pH. Any questions on where any of those numbers came from, why we did anything, any questions that you may have? Yeah, so it was on the previous slide here, so we can go back a slide. Where did I do it? It's right here, I think. Just got to close some things on my screen so I can actually see where I'm pointing to. Yeah, so if you did the assumption down here on the right, so if you did the assumption, which is what we did over here, you got an X value of 0.00917. And if you take 0.00917 and you divide it by 0.15, you times it by 100, you actually get 6.1%, which is technically over our limit there of 5%. So we are going to follow the 5% rule. And like I said, in some cases, it really does depend on the problem, but some cases, it really will come out pretty close if you are a little bit over 5% or not. But you have to have sort of a cutoff somewhere. So for us, it is going to be that 5% rule. So if it's over 5%, you do need to go back and solve it a different way. And that's why you got a slightly different number there as we did. We got 11.94 or whatever, 5 or whatever we got there. But again, sometimes it will be very close, and other times it may not be that close and stuff like that. But I believe the OWL homework will be after the test it's due. I thought I checked it the other day. I think it's like the 30th, believe it or not. Yeah, that should be after the test, I think. Test is coming up on Thursday, right? Definitely going to cover through what we're talking today and maybe some stuff tomorrow. So we'll let you know for sure. I'll double check and see what I got. If it's up there, or maybe it's just not published, I'll double check and stuff. If not, send me an email to remind me if you wouldn't mind, and I'll try to double check when I see the email. Other questions on that? So again, a reminder, as of now, the exam is still coming up on Thursday. Obviously, it'll cover all chapter 13. It'll cover at least through here, and maybe some of the stuff we're going to talk about tomorrow as well. So again, hopefully you're studying with it. And I'll double check the hour. I thought I did the other day, but I think it does say the 30th, correct? I believe. So I think I gave you a few extra days to finish the homework and stuff like that in case you need it. Any other questions on any of that stuff? Okay. So today we are going to do experiment 5, which is our first kind of qualitative analysis experiment. And it's going to be a little bit different. There's going to be kind of the known and unknown. And I think we'll talk a little bit about qualitative analysis at the beginning, some of the techniques that you typically do and stuff like that. And then we'll kind of get into the videos. And you will do a known and unknown today. And, you know, everybody, there'll be different unknowns for people that you'll have to watch and try to identify. Any questions on any of that there? All right, so see everybody about 3-ish. Make sure you come through the lab meeting, and make sure, obviously, if you didn't do so at the beginning and you were here, make sure you type here, okay? Cool. I'll see everybody in about 10 or so minutes. Get up and stretch it a little bit, yeah.